Okay, so let's start. Um, so today we are going to discuss two topics. One is the convolutional neural networks. The other is dynamic time warping. Uh, in convolutional neural networks, let's start. So yeah, why do we need CNNs? Okay, let me first start with general discussion. You have all read about classifiers like neural networks or linear classifiers. Now the thing is, let us see what is a classifier. You have this space which has got roses and lotuses. These are red roses and blue lotuses, right? Now, a linear classifier will be just constructing a boundary like this, or that is basically also the form which neural network also uses. Each neuron is a kind of linear classifier followed by a nonlinearity. And okay, let's look at the form of our. Uh, let's look at the form of the mathematical expression which we get. If you remember, my h is of the form w times x. So let's say w vector dot x vector. Let me use our standard notation where I denote w vector by bold w, and I can say x w transpose x. Right? So this is like a dot product between w vector and x vector. So basically, intuitively, how do you understand is my idea of a classifier is you are storing some pattern in the weights and you are finding that pattern in the input. Whenever the match is high, your h is a large value, right? Your h is like when your w and x. So okay, let us first go back to the definition of cosine similarity. What is cosine similarity? It is basically the dot product, right? Let's say cosine similarity of w vector comma x vector. It will be the dot product, right? W transpose x divided by mod of w vector. Basically, it's a unit norm thing. You can put double or single, right? So this is the basic form, the numerator. So which means if w and x are almost similar, or at least in the same direction they are pointing, then the output will be a large number, close to 1. And if they are pointing in exactly opposite direction, they are same but just different in size, then the output will be a large or -1, large in magnitude. But the output is oblique, means let us say my w is pointing in this direction, w vector, and x vector is pointing in perpendicular direction, then they are the dot product will be 0, right? So basically it's a similarity match. When the w and x are similar, like in the similar direction, w vector and x vector, they're pointing in similar direction, then my dot product will be large. So if x is the input, w is a stored pattern in the model. So basically w has stored what pattern is there in the input, and whenever it finds that pattern, it gives a large output. So that is the intuitive understanding. So let's see how we use that understanding in CNNs, and why do we need CNNs in the first place? Okay, so the problem is of curse of dimensionality. What is curse of dimensionality? If the input dimension, if my x vector is very large, is consisting of lots of, the size is very large, then my classification becomes more involved, which means the size of W also increases, which means the amount of data which is required to train W nicely, that also increases, right? So that is the curse of dimensionality. If my x is very large, then I will need a large amount of data for training my model efficiently. So okay, let me write it down here. Large size X, this implies I need a large size W, or the model basically, if it is any model. And this implies I need large training data to train it properly. So, okay. Now let's see, for image classification, a task like image classification. What is the size of my image? You have read MNIST data. Like last time we discussed about MNIST data, which is images of handwritten digits. So the size was 28 cross 28, if I remember correctly, which means how much? 28 cross 28 is, it was something 720 something, 700 something. Is a large data of the order of 700 size. So for training that, to be able to handle that large dimensional X, I need a large model, and I need a large amount of training data, large number of images. Now let's consider real world images. Like all of you are using cameras. They have, how many pixels are there? It's of the order of millions, right? Million pixels in one image. So which means if your X vector is so large, of the order of million, your model has to be so big, and your training data that is required to train your model will be also very large. That is very inefficient. That is very bad. So can we do something smart to reduce my data requirement and to reduce the size of the model that is needed to classify that data? Let's say I want to classify the image of a person. I know this is the same person, but just that the different pose or different dress color, or different eyes are open or closed, but many things are similar. So of course the entire vector, if you see, entire vector will be different, but locally there are many similarities, right? Local similarities. So the key point here is local similarities. Uh, okay, so now a popular approach which was already used in image processing literature was template matching approach, where we can find blobs or regions that are likely to classify the image. For example, if you look at the mustache, that mustache will be there almost in every image. Mustache is more or less similar. So if I have a template of mustache, and I will, if I scan the entire image with this template, like finding dot product with each and every small window, like I take a small window here and do the pattern matching, the blob matching. Take this blob and take a dot product or whatever distance measure I have, let's say dot product, and I match it over there, I will get some score. It will be low score, low score, low score. But as soon as it finds the window around here, it will find a high score. And therefore, I'm able to detect the mustache. And if I have blobs, many blobs for the same person, which are reliable blobs, then it is very much likely that I can find the person with the help of these blobs, right? The turban will be almost in every image. It will be there. And this hand holding the stick, so it will be there. It is there in this image. In this image, it is not there here, but that's all right. Other blobs will match here. So I can set some number of blobs. Okay, if these many blobs are matching, let's say I have 100 blobs. If let's say 80 of them are matching in the image, then I will say yes, this is the image of the person I'm looking for. That depends. Okay, I'm just giving an example. Okay, so if you look mathematically, it's cross correlation score, like cross correlation of these templates with the test image will give a matching score. You know, the scanning thing is called cross correlation. You have read it in the previous discussions. So now the question is, Okay, this is a very promising approach, very nice approach, which because now my size of my X can be smaller because the dot product which I'm making is a smaller thing, right? The entire image was a large image, but these blobs are very small compared to that. So your data dimensionality of input has reduced significantly. Okay, so yeah, this is the very nice approach. Okay, what next? What problems are there with this approach? Now the problem is, how do I find optimal templates? What are the optimal templates which can discriminatively detect that person? So yeah, that is a question now, how to find optimal templates. That problem is addressed with help of convolutional neural networks, or CNNs. So what CNNs do is they try to find these templates statistically from the data. Like these templates are means these templates are trainable. These templates are parameters which can be trained by your optimization algorithm from the data for the goal of classification in this case, right? And you have read what is training, what is hyperparameter, what is parameter. So if I say these are my parameters, these are like W's, and the original image or the small windows in the image, they are my X, then I can very easily relate it with the neural network architecture which I have already studied. Now, okay, just some small recap on the definition of convolution. Actually, the term used in literature is convolution, but actually it is cross correlation, because the formulation, if you compare with cross correlation, it is because in convolution you invert the input, right? Your input is inverted or your filter is inverted, but in this case nothing is inverted. It's cross correlation. Okay, so this is, I think this is the stuff you have already studied. You have already studied what is 2D convolution. Uh, Okay, and this padding also you have studied also already in the past. Now, how to optimize the kernel for classifier? Okay, so there are some terminology involved in CNNs. I think when you go through the lectures, you will learn these terminologies, like what is a kernel. A kernel is one blob, one template, you can say. And then this kernel will be scanned over the entire image, and that will give you one image. And then you go to the next kernel, that will again scan the entire image, that will give you the next layer, the next output of the next, means the next channel, you can say. And then another kernel will scan, then another channel you will get. So this way you've got here 3 channels, and you can continue this. And finally, this new multi-channeled output which you have received, you can again apply another convolutional layer on top of it, and again do similar multiple kernels, convolve this, and get the output. And finally, what you do is you flatten this layer. Basically, all these numbers, you write them as one vector. Like instead of 3 channels of matrices, you write just one vector. Everything like put serially, but this number, this number, this number. So write everything in the form of one straight vector, and then feed it into a dense network. And then the output of this dense network is what you have already studied. This is basically a classifier layer. It could be multi-class classification or multi-label classification, and you know what kind of nonlinearities you have to use and what kind of loss function you have to use. These things you have studied already in the past, right? Let me open the chat window and see if anybody has any questions at this moment. Okay, there is one comment by Yash Kumar about dimensionality reduction. Yes, so this technique can be also used for dimensionality reduction. Okay, so yeah, now if there are multiple channels in my input, then how do I deal with those channels? Basically, my kernel will also have that many channels, so that I can do a one-to-one product. Like the dot product is possible if my input channel, number of input channels is same as number of channels in the kernel. Okay, now this is something important. So there is some terminology involved with CNNs that is important for you to understand, so that you can understand the research papers very efficiently. I'll just give one example here. Let's say this is my input, which is a single channel matrix, single matrix, and no third dimension. So what I am applying on this is 5 kernels of shape 3 cross 3. So what I get here is I get 5 channels, and what will be the shape here? If you know, this is n. If this is n, and this is also n, then this will be n minus 3 upon 1. Okay, let's say the stride size is 1 plus 1, right? Something like that. Yeah, I think this formula you have derived already. N minus k plus 2p upon s plus 1. So okay, so this dimension will be this much, and this, so basically n minus 2 here, n minus 2 here. And now look at the next layer, convolutional layer. Now here I'm applying 4 kernels of shape 3 cross 3. Same, but there is an implicit channel dimension also involved in the kernels. This is into 5. Why? Because I know my input is 5 channel, so my kernel will also be 5 channel, so that the dot product is possible. Because dot product requires my size of W should be same as size of X. If my input is a small 3 cross 3 window with 5 channels, my kernel should also be 3 cross 3 window with 5 channels, so that I do an element-wise product and then sum over all the elements. That is the definition of dot product. Okay, so now since I have applied 4 kernels, so my output will have 4 channels, and then you can take it further and process it further. Okay, so this is the idea. This is a basic terminology for convolutional neural networks. Now, okay, so there are 2 of my videos which I have recorded for Swayam, which are details of CNNs. You can watch these videos. They will introduce you to various concepts in CNNs. The first video is particularly important, and these are the standard concepts which you will be needing to kind of get a feel of what are CNNs. One is the concept of pooling. One is the concept of dropouts, flattening. Pooling is a simple thing. Basically, what is the meaning of pooling is, let's say if I have got let's say a matrix. Let us say let me write down here. What is pooling? The concept of pooling is this. I have got let's say a matrix, a 2 by 2 matrix. The numbers are 3, 2, minus 1, 5. And if I apply a max pooling to this, a 2 cross 2 max pooling, it means I will take a 2 cross 2 window and I find the maximum number. So this 2 cross 2 window is replaced with a 1 cross 1 window of size 5, the maximum value. And if I apply a min pooling, then what will be the output? Can somebody write on the chat window? Can somebody write on the chat window? Minus 1, very good. And if I apply an average pooling, what will be the output? Can somebody write on the chat window? Average pooling. Okay, good. So basically I average these numbers. So 3 plus 2 is 5, plus 5 is 10, minus 1, 9, 9 upon 4. Yeah, 2.25, good. Yeah, that is average pooling. I think you understood the concept very nicely. In this case, my kernel is a pooling kernel. It is not a multiplication kernel or not a dot product kernel. It's a pooling kernel. And if there are multiple channels, you apply pooling over multiple channels. Basically, let's say here the second channel also has got some outputs like 5, 2, 10, 3. Then accordingly, your outputs will change. Your max pooling result will become 10, and your min pool will remain minus 1 only. and your average will become all these 8 things added up divided by 8, whatever comes out. So that will be your average pooling, right? So this is, so basically pooling is done by a kernel, this operation which applies this operation to the input. And then same things apply, like how do you take the strides, how do you take yeah, strides is the only thing, yeah. So basically hop, which you have already studied in CNNs. Okay, so this is the concept of pooling. Then concept of dropout, it's a probabilistic dropping of different outputs. The reason is to introduce noise, to introduce stochasticity. As you remember, um, uh, so what is dropout basically? It introduces stochasticity. If you remember, if there is a bowl like this and there's a ball here, it may get stuck in some local minima, but if you shake the ball, so shake it vigorously so that the ball goes to the global minimum or a better minimum basically. So you have to shake the ball. This shaking is called stochastic, some kind of stochasticity, and this stochasticity is introduced by dropouts. Basically, a neural network is there. You just randomly drop some outputs, make them zero, right? That introduces some randomness, and that will uh, help in introducing stochasticity into your training. This is done only during training, not while testing. Because while testing, you don't need stochasticity. You only need it during training, so that you can reach the global minimum. Once you have reached the global minimum, then there is no need of shaking or any stochasticity, right? So only while training you apply dropouts. Next is flattening. I've already explained that you you have output as matrix with multiple channels. You flatten it out into a single vector. That is flattening. Number of parameters in each layer. This is a nice concept you can study, how to find the number of parameters in each layer. Depends basically number of parameters in each kernel, right? That will tell you the number of parameters in each layer. Then computational complexity of each layer. How many multiplications are taking place in each layer? This is also very simple. You know, it's a dot product. So as many are the elements in the kernel, that many dot products will be there. Plus one, because if there is a bias element. So plus one for the bias element. And the problem of vanishing gradients. So what are vanishing gradients? Basically, if you have very long network, if you have very long network means multiple layers, at each layer you're multiplying with the output of that layer multiplied with the error, which is backpropagated, multiplied with the uh, uh, non-linearity at that layer, right? And if the non-linearity is small, generally it is a small value. Let's look at the what is it called, sigmoid loss function. The slope of the non-linearity will be zero here, almost zero here, and it has some value only in very small range. So mostly it will be very close to zero. So that will, because of that, your gradients will become very, very small, and it becomes very difficult to train your network, because what do you say, when you find the slope becomes very, very small. That is why delta W becomes very, very small, and your W's don't update much. So that is a problem of vanishing gradients. And if you look at the videos, these two video lectures, you will get a fair idea of what how to avoid these problems of vanishing gradients. And there are some standard practice. I think these you can read on your own. Nothing very difficult about it. The main idea I have explained, that why do we need CNNs? So let's just recap once again. So in CNNs, we want to use the property that a big image, I don't have to find the big image as it is in my, the pattern, same pattern has not to be found, but a big image is like a bag of many small patterns. Like one pattern could be the turban, one pattern could be the mustache, one pattern is the stick and the hand, like that. So these patterns are stochastically found by the CNNs. And now see the beauty that if this turban moves somewhere else, let's say instead of in the middle of the image, now this turban also is here in the side of the image. Again, the kernel will be able to find, because kernel is scanning the entire area. So the kernel will kernel will also hit this area, and it will be able to detect the turban, right? So that is the advantage. It's called shift invariant. So my CNNs, they take care of shift invariance of images. The same thing if it is here in the image, and if I move Sar Chaudhary here in the image, it will still be able to find it out, because my kernel will be scanning and finding it out anyways. Okay. So with this, I think we can conclude the discussion on CNNs. If you have any questions, you can ask. So question from Piyush Gaurav is, will it take care of the size variation of template? The answer is no. How can it take care of the size variation of template? Because if my um, if my template is, let's say, a circle, let's say there is a circle and suddenly the circle becomes small. Now let's say if my template is this big, then of course this it will not be able to find this small circle. But if my template is some small corner of the circle, and it yes, in principle it cannot, but stochastically it may find some features which may remain same when there is when there is some size variation. But in principle, no, it is explicitly it cannot take care of size variation. Yeah, means uh, basically the operation, the dot product operation, uh, is made to be shift invariant, not size invariant. But size invariance can be taken care of uh, because during training you will have many variations of sizes available. So that variation will be learned from the data. It is not inbuilt in the model. I think that suffices. The size variation is learned from the data. It is not inbuilt in the model. But shift invariance is more or less inbuilt in the model. Why do we need pooling operation in CNN? Features are already captured in the template. Very good question. So, okay, the problem is that if I have very large image or very large output of the intermediate layer, to handle that, I will need to perform so many operations, right? Convolution operation is a very costly operation, right? You have to do like this area is getting scanned multiple times, and this area is getting scanned multiple times. So if your image is large, then your deployment time increases. So your with the large input implies your training time goes up, increases, but more importantly is your deployment time. Your runtime increases when during the test or during your deployment. When you deploy your model for the task after training the network, then also when you're running the algorithm, runtime will also go up, because the intermediate layers are so large. So to reduce the runtime, you need to make your outputs small. And how do you make it small? With the help of pooling. With the help of pooling, you can make it small, and that's how your runtime can be reduced. Any other questions? How can we guarantee that pooling will be extracting the feature and not losing any important information? Okay, good question. So since these networks are optimally trained using backpropagation algorithm, that and these templates are also stochastically learned, so it will, while training the network, it will ensure that the features that you get from pooling are the optimal ones. So basically the training will ensure that this should happen. Any other questions? Okay, if not, then we can go to the next topic, which is dynamic time warping. Okay, let me first give you a gist or an intuitive understanding of dynamic time warping. What is dynamic time warping? So, dynamic time warping. There's another question on the chat window from Vishal. He's asking, so feature templates are also learned by backpropagation. The answer is yes. Basically, feature templates are the kernels, and the kernels are your weight matrices or your weights, the weight tensors, which are learned during the backpropagation. Just like in your dense neural network, you have W times X. W are the weights which are learned by during the backpropagation algorithm. Similarly here, your kernels are those weights which are learned during backpropagation. Okay, now coming to dynamic time warping. This is a very interesting area, dynamic time warping. I'll give you some examples to understand. Let us say if I give you two strings. One string is mm, some example. Uh, uh, like presentation. Right? There is a word called presentation. When you are writing, you made a spelling mistake. You wrote, right? This was the original word. And when you wrote this presentation. And your Google will say, let us say, let's take an example of Google search. In Google search, it will immediately say, did you mean presentation? Right? It will immediately say, did you mean presentation? Instead of presentation without an E, it will say, did you mean presentation? So how is it able to find so quickly? So of course, Google is using some other more advanced techniques, but I will tell you one very basic technique which is very powerful. It is called dynamic time warping. So how will you find out? So what you will do is you will match P is matching, R is matching, E is matching, S is matching. One E, this is missing, but N is matching, T is matching, A, T, I, O, and everything is matching. Just one E is missing. So this is I can do very quickly. Instead of finding this word in basically aligning two things. So it's an alignment. Okay, this is one application of dynamic time warping. So how you do it is like this. You will take a matrix. It will have presentation. Let me only write until present so that things are easier. And here, right? And I will say P and P are matching. P and R don't match. P and E don't match. P and S don't match. P and R don't match, but R and R match. E and E also match. They don't match. S and S match. E E doesn't match anywhere, but E matches here. Okay, let me erase this. E matches here. N matches here. T matches here. Right? Now if I have to match these two strings, I know my starting from here and ending from here, starting from here, ending from here, ending here. So what I will do is I will take a path. I have to find the best path starting from here. I have to reach here, and what is the best path I can take, so that my score is maximum, the match is maximum. I will take this, I will take this, I will take this, but I don't find anything here, I can't go back, so I will just skip this thing. I will just go to the next one, skipping this row entirely, and then I will go here. So this means I am skipping one vowel here, one alphabet or one letter here, and I'm just moving in this way. So I will say this string matches this string with only one skip or one deletion. There is one deletion. Only one deletion is there. Now imagine if I ask you the question, if I give you two strings and I ask you which string is closer. Okay, so let me ask you one question. Okay, if I give you two strings, one is Hari, I've taken smaller strings. One is Hare and one is here. I say this is my original string. This is my original string. I ask you, out of, let's say this is x1, the string one, or let me call it s1 and s2. Out of s1 and s2, which one is closer to original? Let me call this as x. Let me call it just as s. So distance between s comma s1 and distance between s comma s2, which is larger? Can you write which is larger? DSS1 is large or DSS2 is large? Which is large? Which distance is large? Which distance is large? Yes, distance of S from S2 is large. Why? Because here you see only, there is only one substitution. But here you have two substitutions. So therefore, ds from S2 is large. The distance is large. Now, there are three kinds of changes possible. One is there could be a substitution. One is there could be a deletion. There could be an insertion also. Right? Three things are possible. So if this is my original string, I can delete something, like in this case, I have deleted E. I could insert something new, or I could replace something, which is basically a deletion and insertion. One deletion and one insertion at the same place, that means a substitution. But okay, I have reduced these two operations and call them as just substitution. So here I have one substitution, here I have two substitutions. Now see, I have found a way to find distance between strings, or in more generally, distance between time series. There are two time series and I can find the distance between them. I can define what do I call as more distance or less distance, but this is generally the principle. Now, dynamic time warping means finding the smallest distance. Okay, if I give you these two strings, Hari and Hare, I ask you what is the least number of operations required to convert Hari into Hare? The answer is only one substitution. But you could also say, I substitute an A with A, an R with R, H with H, I with E. So 4 substitutions. But no, that is not the smallest number of substitutions. The smallest number of substitutions is only one substitution, which which is to change I into E. So how to find the least number of operations needed to convert S into S1. That is called the distance. This is equal to, this whole thing is equal to distance of S comma S1. So Piyush is asking a question. Initially, we would not know what is original. So how we could calculate distance? Okay, you have to assume one as the original, the other as the target. Means one is the source, other is the target, or one is the original, the other is the substituted or the modified one. One is original, the other is the modified. Original modified. And this distance could be symmetric or it could be asymmetric. In our case, it was symmetric. In this case, it was a symmetric distance. Whether you take this as original or this as original, your distance does not change. But you may define it in some other way that it could be asymmetric also. But okay, for the present moment, let us assume symmetric distance. Okay, so this problem can be solved with the help of dynamic time warping. Okay, I think this idea should be very clear. So with that understanding, I think we can go to. So there is a question at how do we know what is the other string? So the thing is, this is called dynamic time warping. So the input are two strings. So the DTW input are two strings, S and S1. And the output is the distance, the smallest distance between S comma S1. Smallest distance between S comma S1. Okay, this is one application. Another application could be application number 2. So this was the application number 1. The second application could be, let us say, if you have a field, it has got, let us say it's a matrix. Let us say you are standing here. I am standing here. This is my current position. And I have to reach here. Or okay, let us say I have to just cross this field. I am here. I have to go anywhere here. I have to reach this wall. And I'm only allowed to take steps diagonally down, right, or diagonally upwards. Or maybe I'm standing on this wall. I'm standing on this wall. I have to reach this wall, and I can move on this wall anywhere. But I can start from any of these blocks, and I have to reach one of these 4 blocks. Means anywhere I can reach. Now, what path should I take so as to maximize the numbers which I collect. I can take this action, or this action. Basically, I can go diagonally upwards, diagonally downwards, or rightwards. I cannot go back. So if I start from 11, I can go to 23 or 35. And if I start from 35, I can go to 19 or 1. I cannot go down. And in this way, I have to start from here, I have to reach here. And which path should I take so that I collect maximum points? Each of these are the points, let us say, or you can say number of fruits in the field which I'm collecting. I want to go from here to here, collecting maximum points or maximum number of fruits. What path should I take? So it's like optimal path finding. So I know my start and end points, but I don't know what path to take. Here, dynamic time warping will be useful. So this, if you consider this, is also, I can formulate as this problem. Basically, I know my start and end points, and I want to find the smallest distance, where here distance means the inverse of points which I take, the negative points which I take, right? Or if you call it negative, I think that is fine. So so if I start at 16, then I go to 35, 19, 20. That's a large number, right? But it's possible some other path may give me better results. I'm not sure. It looks like no, it's, yeah, I think this is the best path. Looks like 16, 35, 19, 20. But how do you find out computationally what is the smallest path which you can take here? So this is another application of dynamic time warping. So I think, yeah, if you go through the theory, you will get to learn many things. So basic form which I would like to discuss with you is this. It's called Bellman's optimality principle. The principle is very simple. Yeah. So to find you want to go from 0 to k. You want to go from 0 to k. Let us take this example. You want to go from 0 to k. Then for any path, the distance, the optimal distance from this point to this point will be optimal distance from this point to, let's say, this point, and the optimal distance from this point to this point. So basically, you are breaking your min operation, the minimum distance operation. Let's say the min of d pi k. This is equal to min of 0 to k minus 1 plus d of pi k. But you are breaking it up. You are saying no, it's just min of d pi 0 to k minus 1 plus min of d pi k. This is the step which is Bellman's optimality principle, which is not obvious, which is not generally valid, but Bellman's optimality principle says that yes, this principle can be used. So using this principle, you can basically find the best path. So basically, in summary, if I tell you what it means is that, okay, let me go to the same example. It means starting from this wall, if I want to come here, basically starting from this 0 point, if I come here, what is the best path? Okay, there is a single path possible. So the best value is 1. Single path possible, best value is 2, best value is 0. So basically, reaching this state, the best possible path will have a score of 1. The best possible path here will have a score of 2. Okay, now reaching here, I want to reach here. I can come from here to here, or I can come from here to here. But this will bring me a score of 6, whereas this will bring me a score of 7. So Bellman's optimality principle says you take this path. So reaching here, you get a score of 7. Let me use a red pen. Score of 7. And now coming here, I can come from here or here. If I come from here, this gives me a score of 22. If I come from here, it gives me a score of how much? 31, which is even larger. So I will take this path, not this path. So my optimal path is my optimal path will be from here to here. Like that, you can construct. And then to reach here, you can come from here, you can come from here, but the best path will be here to here. And then to reach here, the best path will be from here to here. To reach here, the best path will be from here to here. Or no, so actually here to here, not this one. Sorry. It will be from here to here. Out of these three, the best path will come, because to reach here, the best path will be here. So basically, you keep track of your current location, the current token. It's also called token passing algorithm. Token passing. Token means you keep track of the best value when you hit the red value. And to reach here, the best value will be 19. To reach here, the best value will be 35 plus 16, so 40, 51. So at each node, you will get the best path to reach this node, as well as the score of that path. So to reach here, the score is 7. To reach here, the score is 31, I think. To reach here, the score is 19. To reach here, the score is 51. The best path is this. In this way, and then now you want to find what is the best path to reach this node. The answer is, this is the best path, which has a score of 31 plus 7 of 38. To reach here, the best path is 31 plus 25, which is 56. To reach here, the best path is 51 plus 19, which is how much? 70. To reach here, the best path is 51 plus 1, which is 52. Now to reach here, the best path will be how much? 56, right? 56 plus 5 is 61. To reach here, the best path will be 56 or 70, 70, 71. The best path to reach here will be 70 plus 4, which will be 74. To reach here, the best path will be, okay, of course, from 70, so it will be 90. And what is the best path now? Out of 61, 71, 74, 90. The best is 90. So my overall best path will be this 90. And now you can go back, trace back, go to this node, go to this node, go to this node. This is my overall best path. So I just kept track of my local things, and I covered the whole field, and I found the best path finally. So now, how many total possibilities were there? The number of total possibilities was very large, because from here I can go to 2 values. So total number of paths was very large, but this algorithm has made everything tractable. So that is the advantage of dynamic time warping algorithm. I think you can go through the details in the lecture, and I hope if you have any questions, you can answer. You can ask on the forum. So thank you very much. See you on next Monday. And I'm sorry we could not post the assignment last week because of some glitches, but this today or tomorrow we will definitely post the next assignment. Thank you very much. Bye.